So page 38, number 5, we want to find the limit as x approaches 4 of this function. So because it's a piecewise function, I think people typically have an easier time of this if you kind of graph it. So this says that the function is going to be equal to 1 if x is not equal to 4. So if I kind of color code again, that this is a horizontal line at y equals 1 for all of the points except 4. So that horizontal line is y equals 1, and that's true for every point except where x equals 4. And if x does equal 4, we have just a point at -1. So the y value is equal to -1 if x does equal 4. So if we look at this on the graph, we see that as you're getting closer and closer to 4 from either side, the limit is actually just going to be 1. So the limit as x approaches 4, and you can specify from the left and right, but you don't necessarily have to here because it doesn't go on to different functions. So as you're getting closer to 4 from the left, your y values are 1. And as you're getting closer to 4 from the right, your y values are 1. What the function actually equals at that point is a little bit irrelevant because the limit is just talking about what are you getting closer and closer and closer to, not what happens when it actually equals 4. So the limit as x approaches 4 of f at x is just going to be +1. What it actually equals at x equals 4 doesn't matter. You're just figuring out what the y value is as you're getting closer and closer to 4. And you can go 3.999, 3.99999, or 4.00001, and the y values, no matter how close you get, are still going to be 1. And then the next one, page 39, number 11. So sketch the graph of the function and determine the limit if it exists. So I'll do a couple of these, probably not all. I'm trying to figure out which ones are going to exist and not exist. So maybe we'll try B. Here we've got if x is less than 2, that our function is y equals -x plus 4. So that's got a slope of -1, a y-intercept of 4, and that's true if it's up to 2, including 2. So I'm going to see there that f at 2 is equal to 2. So -2 plus 4. So that would be that point. And then -2x plus 6. So this is going to have a y-intercept of 6 and a slope of -2. We could figure out from here, from this equation, you're going to kind of need to know where that open hole would be. So -2 times 2 plus 6 is also 2. So there would be an open circle there with a steeper slope of -2. Probably not that steep, but that's okay. So we see that the limit, because it's approaching the same value from both sides, the limit as x approaches 2 of f at x equals 2, because it's the same from both sides.
So, Mr. Cooper?
Yep.
It's a limit because it continuously goes on, I guess? The line doesn't have a break?
Right, there's no jump. Holes are okay. Like in the previous one, even though it didn't equal at that point. But because if you go along the red path, like the red line going close to there and the blue line, they're both getting closer and closer to the same value.
So if both of them didn't have an equal sign, like if that first one,
Okay, so we can figure out maybe one that's not. I kind of feel like, I don't know, I'm trying to do these in my head. Let's try A. So here we're going to have the line y equals x plus 2 if x is less than 1. So I'm going to color code these. That's going to be green. So it's got a y-intercept of 2, a slope of 1, and it goes to there. And that would have an open circle because it's just the less than. It's not less than or equals to. And then the next one, I'll use all my colors here, is, oh, whoops, sorry. I misread that. That's negative 1. So it would stop before there. The next one, so this may actually be continuous. So the next one is negative x plus 2 if x is greater than or equal to negative 1. So now we still got this y-intercept of 2, but we're going a negative slope. So yeah, this one will not be, that one will be a filled in circle. But the gap between the two pieces, this one won't exist. So the limit as x approaches negative 1 from the left of f at x is 1, and the limit as x approaches negative 1 from the right of my function is 3. Because as I'm going from the left on that green one, it's going towards y equals 1. And as I'm going from the right on the yellow graph, it's going towards 3. So the limit as x approaches negative 1 of the function does not exist because it's different from each side. So you're just going to sketch your graph and then look on the graph what's it going towards at each side of that potential break. And is it going towards the same point like in B or different points like in A? Okay, so page 39, number 13. So f at x equals mx plus b, where m and b are constants. So if the limit as x approaches 1 of f at x is negative 2, and the limit as x approaches negative 1 is 4, find m and b. So the key here is that this is continuous and just a line. There's no holes, no like funny business. No asymptotes, no anything else. It's just a line. So if the limit as x approaches 1 of this line is negative 2, then that means that the point 1, negative 2 is on the line. And if the limit as x approaches negative 1 is 4, then the point negative 1, 4 is on the line. Like we know if this is a y equals mx plus b, it's not going to be doing any weird things or like having jumps or being piecewise function or asymptotes or holes. It's just a regular line. So you're just looking for the line through these 2 points. So you would just do the slope, 4 plus 2 over negative 1 minus 1. So the slope is negative 3. And then y equals mx plus b. you can use either point. -2 equals -3 times 1 plus b. -2 plus 3 is b. b is 1. So it's the line y equals -3x plus 1. So the only trick here really is that you have to identify if it's a line, like they tell us, that these limits are really overcomplicating things, because you don't really need to use limits to define points on a line. It's just a straight line. If it's getting close to that point, it's going to hit that point. There's no kind of tricks in a line, like no asymptotes, no holes, nothing that's going to disrupt that. Okay, and then number 7 feels like this was D, E, and F. Okay, so D, we have the limit as x approaches 0 of 2 minus the square root of 4 plus x over x. And whenever we have like square roots with the adding and subtracting, you're going to want to rationalize or multiply by the conjugate. So 2 plus the square root of 4 plus x. That plus is kind of sideways. Over 2 plus square root of 4 plus x. So here we've got the limit as x approaches 0. And when I FOIL this out, you're going to lose the middle two terms. So 2 times 2 is 4, plus 2 times the square root of 4 root x minus 2 times the square root of 4 root x. I'm not going to rewrite that every time. Minus 4 plus x in brackets over x times 2 plus square root of 4 plus x. So we get the limit as x approaches 0 of 4 minus 4 is gone, and then minus x is left because that negative will FOIL in there, over x times 2 plus the square root of 4 plus x. And then we can reduce and get rid of the x on the bottom that was causing us trouble, and we'll just have a -1 on the top. So we get the limit as x approaches 0 of -1 over 2 plus the square root of 4 plus x. When you're ready to drop, or when you're ready to sub that x in, x equals 0, then you stop writing the limit notation, but not before that. So we get -1 over 2 plus the square root of 4 plus 0. -1 over 2 plus the square root of 4 is 2, so -1 over 4. I'm going to add in a slide and we'll do E and F. So I'm just copying these ones down on the next slide. Here. Okay, so then E, same idea, multiplying by the conjugate here. It's going to be root x plus 2 over root x plus 2. So the limit as x approaches 4. So when I multiply this out, I'll get root x times root x is x, plus 2 root x minus 2 root x disappears. I'm not going to write them. Then minus 4 over x minus 4 times root, oops, that square root's just on the x, root x plus 2. And then your x minus 4s will cancel out, and you'll be left just with a 1 on top. So 1 over root x plus 2, and then you're ready to sub in. So you stop writing the limit signs. And we get 1/4. Okay with that, guys, so far? So then the next one, same idea. We're going to conjugate this. So 7 minus x plus root 7 plus x. And that's a lot of like sign changes in there. I'm not surprised that could mix people up. So here we're going to have root 7 minus x times root 7 minus x. And that's going to give you just 7 minus x. And then we'll have plus that one and minus that one, and they're the same. They're always the same if you do the right conjugate. Then we have minus 7 plus x. And you never want to multiply in on the bottom. Because we know we need to reduce out that x. So here we've got the limit as x approaches 0 of 7 minus x minus 7 minus x. Everything else staying the same. 7 plus x. So those will disappear, and I have negative 2x over x times this same stuff. Whoops. Bracket. And then the x's will cancel, so we'll have the limit as x approaches 0 of just negative 2 over root 7 minus x plus root 7 plus x. Then we're ready to sub in, so we've got negative 2 over root 7 minus 0 plus root 7 plus 0. So negative 2 over 2 root 7. That will reduce, and then I'm going to multiply by root 7 over root 7 to rationalize the denominator. So negative root 7 over 7. Now, this one is probably like the biggest, most terrible rationalizing that you could have to do. This would not be on a test. It ends up being really, really super huge. But what we actually have to do is multiply by the conjugate of each one of the numerator and denominator. So the best way I have seen to show this, or the way that I think makes the most sense to the most people, is to color code this, and I always color code things. So I'm going to multiply by the conjugate of the numerator first, and I have to do that top and bottom. So I'm going to multiply by root x plus 1 plus root 2x plus 1. And normally I would put the conjugate, or like that same thing, right on the bottom there. But I also am going to have to do the conjugate of this big mess. So I'm actually going to put this like equal one that I've done in blue over here to show that I'm not going to multiply it in on the bottom, because I know it's not going to actually reduce things on the bottom. I'm going to like leave it off to the end. And then sort of similarly, I know I have to multiply on the bottom by the conjugate. So that's root 3x plus 4 plus root 3x plus 4. And I know I have to multiply on the top to keep that balanced, but I'm going to do it off to the end where it's like out of my way and not going to get involved in the question. So then root 3x plus 4 plus root 3x plus 4. So now these are the ones that I'm going to actually FOIL out, and I'm going to leave this stuff for the very, very end. So I'm going to multiply here first. So here I'm going to get root x plus 1 times root x plus 1, which is just x plus 1. And then a minus and a plus, and those middle terms are going to cancel out. Then I'll have minus 2x plus 1. So that's what I get on the top of the first two fractions. Then I'm going to do the same on the bottom. Root 3x plus 4 times root 3x plus 4 is just 3x plus 4. And then I'll get 1 minus 1 plus that'll kind of cancel each other out, where I kind of go like that. And then I'll have, oh, whoops, I just noticed that I did 2 the same, and the second one is a 2x. Oh dear. Okay, so then we're multiplying down here, and we get minus the 2x plus 4. So that's the bottom there. And I still have this last one that I just left out at the end. 3x plus 4 plus root 2x plus 4 over root x plus 1 plus root 2x plus 1. So we kind of did like a double conjugate there. And then we're really just going to leave that one at the end out and simplify inside this first set. So here I get x plus 1 minus 2x minus 1 over 3x plus 4 minus 2x minus 4 times that same thing. I'm just going to focus on this first one. That the ones would be gone, and then I have negative x over x times that same bracket, just kind of for saving space. So here I get the limit as x approaches 0 of negative 1 times this bracket with the square root 3x plus 4 plus the square root 2x plus 4 over square root x plus 1 plus square root 2x plus 1. And then we can actually sub in the x equals 0. So I have negative 1 times the square root of 3 times 0 plus 4 plus the square root of 2 times 0 plus 4 over root 0 plus 1 plus root 0 plus 1. So in here, 3 times 0 is 0, plus 4 is 4, square rooted is 2. So on top I have 2 plus 2. On the bottom I have 1 and 1. So that all together gives you negative 2. So that's a real big, messy one. And that would be bigger than you would get on a test, but it's still a good idea to kind of understand where that comes from. Okay, so the next one is, this is actually one of the limits that we did in the derivatives from first principles lesson. So we've got the limit as h approaches 0. We're just going to FOIL out on top, and things will cancel and life will be good. So I'll have x squared plus 2xh plus h squared minus x squared over h. Then reducing the x squareds. And I'm going to factor out an h. So I have 2x plus h over h. And those h's reduce. And then when you're ready to sub in, you drop your limit notation. And we just get 2x. So that one probably felt more weird with having the multiple variables like the x's and the h's. but hopefully better after the next lesson. Oh, and this one can be a little bit tricky. It is going to be one of those substitution ones. And I think the trick here is figuring out which thing is worse, I guess, to substitute into, to get rid of. And I feel like this x to the 1/6, the 6th root of x is messier and like objectively harder to simplify than the cubed root of x. I feel like we're maybe more comfortable with the cubed root. And it doesn't have to go this way, but I think that it's easier if we do. So I'm going to say let u equal x to the 1/6. So then I'm going to have all of the same pieces, but I'm going to leave some blank. So the limit, I don't know what's happening down there, but I'll have u minus 1 on top. And on the bottom, I don't know what's happening to my x to the 1/3 minus 1. So remember that we have to kind of go through all of the steps of replacing each part. So I wouldn't actually write these boxes. That's just to kind of remind you what we've got going on. So we would then know that x would equal, that's going to be u to the exponent 6. So where I have the x, I've got something to the 1/3. I'm going to put u to the 6 in there. And we'll have to simplify that a little bit. So we also see that as x approaches 1, if u is 1 to the exponent 1/6, u is actually approaching 1 as well. So that's not common. But in a case like this, it can happen that the variable in the limit doesn't actually change, or the value of that. So I'm just going to simplify a little bit, that I have u minus 1 over, now this is like exponent rules, right? 6 times 1/3 is 2, so it's u squared minus 1. And then that's not too bad, just a difference of squares. That will reduce, and you've got a 1 on top. So I kind of put that right in the middle, and I will need a bit more space. So I have the limit as u approaches 1 of 1 over u plus 1. Now I can just drop that, and it's 1 over 1 plus 1, or 1/2.